what we've done so far, just to kind of frame big picture of what we've done so far. We have looked, and we started out looking at the idea of the time value of money for simple interest. Now, simple interest is interest that is not compounded, and it's usually for loans or borrowings that are less than 1 year. There are some examples where it goes over a year, but the majority of them are for less than a year. And we saw the various formulas in that. There were basically three. The time value of money formula, which is I equals PRT, or permutations on that. And we also saw the future value and the present value formula, PV 1 plus RT, that formula. You've seen the iterations of that. And we calculated the future value and the present value for simple interest. That was the first thing we did. And then we moved on to part B, and part B introduced the concept of compound interest. And compound interest is usually for loans that extend past a year. And as we've seen, I think it was Lori asked the question, but with regards to the issue of compounding, and what we have to do with compounding is there's another little step that we need to take where we have to figure out how many compounds per year affect this particular calculation. And compounding can be daily, weekly, monthly, semi-annually, yearly, and all of those equate to a certain number of times a year, 365 times for daily, 12 times for monthly, 52 times for weekly, and so on. We have to figure out how many compounds per year. And we also need to calculate how many years in total is the loan for. And based on that, we can calculate the total number of compounds in the loan. And that total number of compounds in the loan is used to calculate M, which is a exponent calculator. And we also need to take the interest rate that is on that loan, because interest rates are stated annually, and we need to divide it by the number of compounds per year. In other words, we need to get the interest rate per compounding period. We throw all that into a formula, and we can do some things. We can calculate the future value, and we can calculate the present value of a particular loan that is using compounding interest. And we can do a whole bunch of things with that. We talked about things like, okay, we can look for equivalent values. And one of the things that we spent a lot of time on was this issue of looking at loans that are replacement loans for existing loans. So we're trying to figure out, well, what is the equivalent value that would leave someone in the same basic state. So that's what we've done so far. Okay? What we're doing now is the next kind of iteration. So it's like walking up the steps. This is something called annuities, and annuities are very, very common in business. We never hear the term annuities. Annuities is kind of an unusual term, but effectively what an annuity is, by any other name, is a stream of equal payments. So you know how you see the commercial on TV for the Atlantic Lottery, and they give you set for life? You know, the one that's set for life. So they say, okay, you can get, I don't know what it is exactly, $25,000 a year for so many years, right? That's an example of an annuity, because they'll give you $25,000 a year, say for 25 years, okay? Instead of life, let's put a hard date on it. So you're getting $25,000 a year, every year, for 25 years. And you're kind of perplexed. You're saying, well, that's $25,000 a year. That's neat. But how much is that worth now? How much is it worth now? What if I took a lump sum payment now? And you hear tell people taking a lump sum payment. Well, that's really what we're doing here. The calculation of annuity is figuring out what is the value of a stream of payments, a lump sum payment, in other words, is what we're looking for a series of payments. And you think about it, you know, you go get a loan for a car. I know some of you might have loans for cars, houses, or things. What you're doing is you're paying a set amount every month, whatever. And at the end of a certain period of time, say 60 months, the loan is paid off. Well, that's an annuity. Most loans are annuities. Annuities are very, very common, but we never hear them called annuities. We normally hear them called loans or some sort of thing. So the basic crux of what we're looking at now is saying, okay, how much is something worth, if it's worth today, if there's a stream of payments involved? Okay, so really that's really what we're looking at, is kind of figuring out, let's bring it down to how much is it really worth, and that way we can compare things. So annuities are common in the insurance and retirement business. An annuity is simply a series of equal payments made at regular intervals over time. So wages, rent, mortgage payments, insurance premiums, and the like are all practical applications of annuities. So annuities differ from regular compound interest because the money is continuously paid. So there's a flow of payment as opposed to a payment here and a payment there and a payment there. So this part of the unit, we're going to look at that. So here specifically now is the breakdown of all the things we're going to look at. We're going to apply the compound interest in order to calculate this annuity thing. We're going to distinguish between something called a simple and a general ordinary annuity. Now, annuities have this extra little wrinkle put in them where the compounding period, okay, so how many times it compounds, and the interest could be a different on a different schedule, we'll call it, on a different schedule. And if it's on a different schedule, that would be what's called a general annuity. If it's all on the same schedule, it's a simple annuity. We'll get into the details of it now in a few minutes, but just take it from me that there are two types of annuities. One is a simpler one, and the other one is a little more complex, and we have to do some additional calculations for it. We're going to distinguish between an ordinary annuity and an annuity due. So as we move through this, we're going to look at something called an annuity due. An annuity due is just another little wrinkle that's added to it that says, okay, the payments are made at the beginning of the period as opposed to the end of the period. Normally we assume that, you know, when we get a loan for a car, for example, you go buy the car and then you make a payment at the end of the first month and the second month and the third month and so on. So that's what's called a general regular annuity, where we just kind of get the car, got it for a month, and then we pay it. Okay, and then the stream of payments start. An annuity due is when you make your first payment right away, and the stream of payments start. So there's this little slight difference in where the schedule starts. And there's a little bit of a change in the not a major change in the calculation, but you need to recognize the difference between an annuity and an annuity due. The mechanics of the calculation are basically the same. Calculate the future value of an annuity, present value of an annuity, same thing we've done with all of these, and the knowledge of the compounding applications. And really that's the critical thing, because as we go through this, you're going to say, how can I apply this in the real world? Because otherwise it becomes a mechanical exercise, okay? So I don't want you to think this is a mechanical exercise. This really goes on all the time in the world when we get a loan or we buy insurance and this sort of thing. Annuities are a very common mathematical calculation. Granted, most of the time we're using a computer to do it because the calculations can be a little bit tedious. But we have to understand the underpinnings of it. So as this is an introductory course, here are the underpinnings. Okay, there's some terminology that we need to be aware of. The first thing we need to be aware of is the payment interval. And that's really the time between the payments. So a monthly payment, semi-annual payment, yearly payment. So that's all that means. And, you know, payment interval comes into play in the calculation of the annuity. The term of the annuity. Now, the term of the annuity is how long this stream of payments go for. So the time period between the first payment and the final payment. So a 5-year loan, for example, so your payments go on monthly for 5 years, there's 60 payments. That's the term of the annuity. Frequency. Frequency is the time between intervals. So frequency would typically be a payment annually, a payment semi-annually, a payment quarterly, monthly, bi-weekly, weekly. You could think of your pay, for example, as a bi-weekly type thing. And then a payment itself, PMT, which is the actual payment. And as I said, the payments can be made at the beginning of the period or end of the period. An annuity due is a beginning period payment, and an annuity is an end of period payment. And N, which is one of the wonderful letters that you'll be introduced to, is the number of payments in the annuity itself. So we got some terminology there that we need to get a hold of. So you can see in that little graphic here how this works. You got a timeline, and you got your various payments, the PMTs there. The total term of the annuity is the whole stretch. The payment interval is the distance between the first and the second, or second and third, whatever. And that interval is more or less set. And each interval will have an interval number. So, we've got a situation, you can think about, you ask yourself, here's a simple one, where you're gonna, let's assume it's monthly. So here's now, and along the timeline, in 1 month, you're gonna get $100. In 2 months, you're gonna get $100. In 3 months, you're gonna get $100. In 4 months, you're gonna get $100. 5 months, let's assume it goes out for a year, okay? So you got a stream of payments. Now, you and I can calculate that very easily in our heads to say, okay, look, you just said that you're getting $100 a month for a year. Well, there's 12 months in a year. 12 times 100 is $1,200, right? Okay. And that'd be fine if there was no such thing as the time value of money, or interest was zero, right? So $100 a month, 12 months, voila, $1,200. So if you ask yourself, what would I accept now, as opposed to waiting for all those payments to come in and assuming no interest rate, the answer would very easily be $1,200, right? But we know that there is such a thing as interest, and there is such a thing as the time value of money. So our calculation needs to take into account the fact that because there is time value of money, this $100 is going to be worth more than this $100, because this $100, the one on the right, is further out. So effectively, we need to be able to draw all that back to now, those 12 payments in my example. Those 12 payments, we have to draw them all back to now, assuming a rate of interest. Okay, a rate of interest, and we know the payment. So that's basically what we're doing with annuity. Now, here's the hardest part in this concept of annuity, okay? It's this potential out of kilter in terms of how we calculate it. So annuities can be classified on 2 criteria. First, when the annuity payment is made at the beginning or end of the period. We talked about this idea, this being an annuity versus an annuity due. An annuity due is made at the beginning of the period, and an annuity is when the payment is made at the end of the period. And the compounding frequency of the interest for the annuity. So, you think about the interest and you say, well, we got 5% compounded semi-annually, that sort of thing. So that comes into play. And we have to ask ourselves, okay, let's assume that the interest is compounded monthly. Okay, the interest is compounded monthly. And let's assume that the payment is made monthly. So we've got the compounding of the interest monthly, and the interest monthly, or the payment monthly, sorry. The compounding interest is monthly, and the payment is monthly. Monthly and monthly, they're the same. Okay, that's what's called an ordinary simple annuity. And you can see in the little chart below, an ordinary simple annuity. The payment is made at the end of the period, and the interval and the compounding frequency are the same, monthly. Now, we could have a loan that has, for example, a payment that's once a year. So we've got this simple loan, we make a payment once a year, but the interest is calculated on a monthly basis. So the payment interval is 1 year, and the compounding period is once a month. Okay, so we've got this kind of slight difference. And because there is a slight difference, that's what's called an ordinary general annuity. And the ordinary general annuity needs one more step in the calculation. Otherwise, the mechanics of it are pretty much the same, but there's one more step that you need to do. So you see an ordinary general annuity, the payment is it's made at the end of the period, and that the interval to the compounding frequency is not equal. And then we got the variation, the other two variations, which are just variations on the first two, where the payment is made at the beginning of period, and the interval and the compounding frequency are the same. So that corresponds to an ordinary simple annuity. But in this case, it's called an ordinary simple annuity due because the payment is made at the beginning of the period. And the general annuity due is when we've got at the beginning of the period payments made, but is not equal in terms of the interval and the compounding frequency. Seems more complicated than it is, but very first thing we need to do when we get into a problem here is we need to ask ourselves, when we assess the problem, what type of annuity is this? And really, the annuity will fall into one of four categories. It will be an ordinary simple, it will be an ordinary general, it will be a simple annuity due, or a general annuity due. We need to be able to distinguish each of those. Okay, that's going to be important for the calculations. We're going to be doing one of them. We're going to be doing each one of these in sequence. But on an exam, you're going to need to be able to look at it and say, okay, which type is which? The very first one we would need to take a look at is this concept of ordinary simple annuities. So ordinary simple annuities are used to calculate the future value or the present value. So one is looking forward in time, the other one is looking back in time, of a payment stream that's made at the end of the payment interval, and when the payment interval and the compounding frequency are the same. So this is this first type, okay? This first type. So that's the criteria there that we need to be able to distinguish in our minds. What exactly do we have? So it's typical that it be the future value calculation is a common one to ask. How much do we have if we're saving money? Usually a future value is a saving money. So you're in a situation, say for example, you put 5,000, I'll use the same numbers as here. You're going to put $5,000 in the bank for 5 years. Okay. You're going to put the money in the bank for 5 years, and you ask yourself, how much are you going to have at the end? Assuming an interest rate of, and I don't know what it is here, 10%? 10%? Yeah, 10%. Assuming an interest rate of 10%. So here, we can calculate, we've used this formula here already, FV equals PV. And really we could use that formula. It just gets cumbersome because what we got to do is we got to say, okay, look, here's our first year. So we're going to take $5,000. It's going to sit there. It's going to sit there for 4 years. 1, 2, 3, 4. Okay. It's going to sit there for 4 years, and it's 10%. So we can run it through this formula right here, the formula that we've been using all along for compound interest. And we will get, that's 5,000 will grow to 7,321. And we can look at then the second one, the year 2, and it's going to sit for 3 years. And we're going to take it and we're going to say, okay, 10% interest on it. And I think it's compounded annually. You notice that there's 3 compounds there. So that's 6,655. So we do that for each of those. We add them all up and we get the total amount of money that you're going to have in the bank after putting $5,000 a year in the bank. Now, keep in mind, we're going to put 5,000, 5,000, 5,000, 5,000, and 5,000, which is $25,000. We're putting $25,000 in the bank. But because of interest, we calculate that the total amount we're going to have after 5 years will be $30,526 at 10% interest. This calculation will work fine. We could do this with our existing knowledge of compound interest, okay? The thing is, as you are well aware, this can get a little gruesome if we had 100, or if we had 300, or even if we had 20. We only have 5 here, 5 periods, so it's relatively straightforward. But as it grows, wow, it gets kind of cumbersome. So what we need to be able to do is to find some sort of a formula that allows us to do this for any period of time without having to do all of these simple calculations and add them all up. And voila, here's the formula. So the formula, again, looks more intimidating than it actually is. In order to figure out this same problem, okay, we put $5,000 in the bank, 5 years. At the end of the year, how much you want to have if it's 10% interest rate at the end of the period. So that was the basic question that's being asked. We could use this future value of an annuity formula, a simple annuity, and we are going to find the future value, the payment, which we are paying what, $5,000 a year, okay? 1 plus I, and the interest rate is, in this particular example, 10%, 0.10. N is the total number of periods for which the annuity will last, that should be, so right? So it's 1, 2, 3, 4, 5, minus 1 over I, and again, I is the interest rate, which is 0.10. And if we did that, we would get $30,526. We would get the exact same answer. Here's a fuller example that you'll also find in your textbook. Heinz has contributed $300 at the end of each month for the past 15 months to a savings plan that earns 6% compounded monthly. What amount will he have 1 year from now if he continues with the plan? Okay. So first and foremost, we have to look at this, and I'm just going to hop back a couple slides here. The ordinary simple annuity, by definition, has payments made at the end of the period, and the interval to the compounding frequency is equal. Let's just see if that actually matches in this formula. Okay, we know the payment, and the payment is made at the end of each month. That's the end of the period. That, by definition, means that it is an annuity as opposed to an annuity due, which would say at the beginning of the period. Okay, so this is an annuity. And it says for the past 15 months to a saving plan that earns 6% compounded monthly. So we got monthly payments and monthly compounding. Because that's monthly, the payment stream and the compounding stream are equivalent. In other words, both are monthly. That's what we define as a simple annuity. Okay, both of those are the same. The simple annuity again uses this formula, and this is the same formula as there. So we're taking, in order to find the future value, we have to, well, it's 15 months gone by, and we're looking for 1 year from now. So it's 15 plus 12, right? 15 months behind us plus 12 ahead of us. We want to know what it's going to be at the end of the period. So that's 27 months. So 300, it's 6% compounded monthly. So we have to do the same thing we've done in, we have to do the exact same thing we've done in the compounding. We know that 6% compounded monthly, so that's 6% divided by 12. That will give 0.5%, which is 0.005. Hence, this is where this 0.005 came from. To the 27, which is the total number of compounds. Okay, so this is, again, Lord, is to your point, this is over the course of the whole thing. There's 27 periods, 27 compounds. Minus 1 over 0.005, which is the interest. Do the math on that, and that comes to $8,649.11. In other words, at the end of the period, if we drew a timeline, and we're asking what's going to be at the end there would be $8,649.11 in the plan. Here's another potential type of question. Paulette and Ruby each contributed $100 a month in 2 different investments. Paulette made a regular monthly contribution, earning 5% compounded monthly. So again, we've got this, she made regular monthly contributions and compounded monthly. We know this is by definition a simple annuity, and it's made at the end of the month, for 20 years, well, Ruby found an investment that could earn 15% compounded monthly, so she decided to contribute for only 10 years. So we've got the total length of time here, a little bit different, based on the future value of their investment plans when they each mature, which has a greater impact on the future value of investments, length of time, or interest rate. Well, let's take a look. All we're doing is really calculating for Paulette first. So Paulette made regular monthly contributions, 5% compounded monthly. We need to take 5%, divide it by 12, and that will give us 0.416 rate per month. And it's for 20 years. So keep in mind, it's compounded monthly for 20 years. So that's 12 compounds a year times 20 years. 12 times 20 is 240. Okay. So we plug that into the formula. So it's $100, 1.00416, which is the interest rate per month, I, to the power of n, which is the total number. So that's 12 times 20, 240, minus 1 over 0.00416. Do the math on that. That comes to 41,103.37. So that means at the end of doing all that she's done, making those contributions of $100 a month, for 20 years, she'll have $41,103.37. That's what Paulette has done. Ruby found an investment that could earn 15% compounded monthly. So she decided to contribute for only 10 years. So again, 10 years compounded monthly. So that's 12 compounds a year times 10. 12 times 10 is 120. It's the total number of compounds. 15% divided by 12 will be 1.25% per month, which is 0.0125. So this gets plugged into the formula. $100 payment, 1 plus 0.0125 is 1.025, to the power of the total number of compounds, which is 10 times 12, 120, minus 1 over 0.0125. Do the math on that. That comes to $27,521. So Paulette is getting $41,000. Ruby is getting $27,000. Well, it seems like Paulette is going to get a much bigger, have much bigger savings here. In fact, the difference is about $13,500. The length of time investing has more of an impact on the future value of an investment than the interest rate. And the answer why that is the case, because compound interest is interest on top of interest, and the longer you save, the greater the impact of interest. So it's what we call an exponent curve. Even though you can't see me drawing here, I'm drawing a line that goes up. So as it gets older, more and more money grows. We also have a scenario where the rate may change during the period. So calculate the future value of an ordinary annuity with payments of $600 every 6 months for 16 years. The rate of return will be 3.5% compounded semi-annually for the first 5.5, and 5% compounded semi-annually for the subsequent 10.5 years. So again, the very first thing we need to do is check to see if this is an ordinary simple annuity. And by definition, the ordinary simple annuity says in order for it to be an annuity, it has to be a payment at the end of the period. So all indications here, there's no indications is made at the beginning of the period. So if it doesn't say anything, you assume that it's a simple annuity. Okay, so you assume it's an annuity as opposed to an annuity due. We have to check to see if it's simple annuity. We got every 6 months is the payment, and compounded every 6 months. Semi-annual means every 6 months. So they're both the same, every 6 months, every 6 months. So by definition, it's an ordinary simple annuity. And all we need to do is to be able to do the math on that. So in this particular case, we've got really, we could look at it and say, this is 2 separate loans. The first loan, is at a certain interest rate. The second loan is at a different interest rate. So all we need to do is look at the first one first. Okay, the first one first goes up 5.5 years. So we're at $600 every 6 months and 3.5% for 5.5 years. So we're saying, okay, 5.5 years times 2 compounds. 5.5 times 2 is 11. So the total number of compounds for the first one is 11. So this is $600 and is 11. That will bring us up 5.5 years. And then from 5.5 to 16 years, it switches from a 5% compounded semi-annually. I got to make sure I'm reading it right now. In the first 5.5, and for the subsequent 5% compounded semi-annually for the subsequent 10.5 years. Yeah. So semi-annually, we got to, that's 2.5%, 5% divided by 2, which would be 2.5% per, and we've got a total of 10.5 years. 10.5 years times 2 per year is 10.5 times 2 is 21. So the total number of periods is 21. So effectively, these are the key things that we have here. We've calculated the first one, and then that's going to give us the value at this point in time. Then we're going to take that value there, and we're going to bring it up to 16 years. So here's the math on that. So we got to calculate the first future value here, so $300 a month. So we do the math on that, and that's 300 is the payment. The the value of I is 0.006. 1 plus 0.006. There's the total number of compounds. Okay, is gonna make sure I got this right now in terms of my head. Yeah, I've got something wrong here. I got the wrong. These are not right in terms of they're matching. Okay, I made a mistake. Just bear with me while I figure out why I've done that. Anyway, I made a boo-boo. But I made a boo-boo in terms of I got two different problems. I got this problem here and another problem here, and they're not the same problem. But the mechanics of it is exactly the same. We've got to calculate the value to here. So we do that by using this formula. We plug the appropriate numbers in, and we will get a value at this point right here. Then we're going to take that value and we're going to apply the next set of information to it. So basically, that value then will create the next formula, and we will find the total there. I'll have to get that fixed. I'll look to get that fixed. That's a boo-boo on my part. But effectively, we do two separate calculations to find this future value. Okay, so that's that one, and I'm going to hop past that one. Now, this is, I will tell you, this is a pain in the butt to do with your calculator. This is a pain in the butt. It is not impossible. It is just so prone to rounding errors and so prone to finger errors, which I always do. I press the wrong button or do something like that. So one of the things I've done, as much for you to check your numbers as anything, is I've created a spreadsheet. And now this is my creation. You're going to say it might not be very good, but it works in terms of the mechanics of it. And I have the link here. And effectively, what you do is you identify what type of problem it is, in this case, an ordinary simple annuity. And I ask you to include the key material. So you just basically plug the numbers in here. So the payment period, the annual interest rate, compounds per year, payments per year, and I say must be the same. And by definition, an ordinary simple annuity must be the same. Total number of years. And that little spreadsheet then will calculate what the value of I is, which is the interest rate per period, and it will tell you the total number of compounds, and it will write the formula for you. So FV is the payment times what I call the numerator and the denominator. Numerator and denominator is this bit here and this bit here. And it will give you the future value. So what I do is I just use my little spreadsheet to go through and get the answers very quickly, and it just double checks. Well, let's take a look at some of these problems here that I've got pulled out of the book. Okay, these problems are in the book. If you're wondering where I'm getting this to, it's right in your textbook. So the first one, it says this problem demonstrates the dependence of an annuity's future value on the size of the periodic payment. Suppose a fixed amount will be invested at the end of each year, and the invested funds will earn 4% compounded annually. What will be the future value of the investments after 25 years if the periodic investment is $1,000 per year, $2,000 per year, $3,000 per year? Okay, so what we're asking here, what's being asked here, is for you to do 3 calculations effectively. And the first calculation is the payment, PMT, is $1,000. Okay, that's the first thing you're going to do. The other bits of information that we have is that the investment earned 4% compounded annually. Now, little check that should go off in your head. All of them now will be a simple annuity due. The compounding is annually. The payment is annually. That, by definition, is a simple annuity. Okay? So 4% compounded annually is 4% divided by 1, so I is 4% or 0.04. And it's 25 years, so the total number of years is 25. And if we figure out how many compounds there are, 25 years times 1 compound, 25 times 1 is 25, so N is 25. So we can plug those numbers into, let me go back to the formula. We can plug those numbers into this formula here to find the total value at the end of the period. So the question 1, what we're looking at is it's asking us to calculate the total value after 25 years. Okay, so what's the value of the investment after 25 years? Assuming $1,000 is put in a year, and assuming 4% compounded annually. Okay, so what we do is we need to be able to get the numbers straightened away first. The N, which is the total number of compounds, is 25 years times 1 per year is 25 compounds. The I is 4% divided by 1 per year, one compounding period. That's 4%, which is 0.04, and the payment is 1,000. Here's the formula. FV equals PMT, 1 plus I to the N minus 1. So we just throw the numbers into the formula. 1.04 is 25 minus 1.04. This works out to, if you do the math on that, that's 1.665836 over 0.04. And that comes to $41,645.91. So in other words, if we put $1,000 in the bank for every year for 25 years and it earned 4% annually, at the end of the period, at the end of that 25 years, it would be $41,645.91. Okay. Then the second part of the question says, well, let's say that you put $2,000 a year in. Now, I haven't worked it all out. I haven't written all this down again, but we're just taking that number there and putting a 2,000. Everything else is the same. So it comes to $83,291. And it comes to, for 3, to $124,937.72. Now, I'm just going to go out now and I'm going to show you. I'm going to switch gears here now. As I mentioned back here, I have this little spreadsheet done up. And I'm going to go bring you to that now. I'm basically going to resolve this problem. I'm going to do this formula in the spreadsheet. So let me just switch screens here. So here we have the ordinary simple annuity, which is what we're dealing with, and we're calculating the future value of it. If we go back to our problem, and instead of me switching, I'm hoping you see that. Yeah, you can see that. I'm going back to the problem, and I know that the payment in this case is 1,000, so I'm just going to put 1,000 in here. The interest rate is 4%, just 4%. The compounds per year, if I look at the problem, there's one compound per year and one payment per year. In the case of an ordinary simple annuity, these must be the same as I've indicated here. And it's for 25 years. So this then generates, in the red, it generates this interest rate per period is 0.04. So it basically takes 4% and turns it into a decimal. Number of compounds, 25 years, 25, one per year is 25. The future value then is 1,000 times the numerator, which is this the crazy calculation there, divided by I, and it'll come to 41,645.91. So let's take a look at number 6. Okay, I hope you have a sheet of paper or something. And I just want you to try this and write down the pertinent bits of information. So the pertinent bits of information on this particular problem is that the amount of money invested is $75, okay, at the end of every month. So the $75 is your payment, and it's at the end of every month. This is what we would call an annuity then. Every month, so every month we've got that payment, okay, for 2.5 years, 2.5 years. And so if I think about 2.5 years now times 12 months in a year, that's really what I'm saying there is that's 30 payments. Calculate the future value of the funds earned if it's 8% compounded monthly. Okay, well, the payment is monthly and the compounds are monthly. So this is what's called a simple annuity. We know that monthly and monthly there, it's a simple annuity. So we've got our little bits of information here. The 8%, we have to convert that now. That's 8% compound monthly. So we take 8%, divide it by 12, and that will give us the value of I. Okay, so 8% divided by 12. So just hang on now. Okay, so the 8% divided by 12, then in a decimal format, it was 0.0067. And the total number of periods, a total number of compounds would be 30, so N would be 30. So we could really plug that into that basic formula. So what I'm going to do now is I'm going to give you guys a few minutes. So here's the basic information. We got $75 as the payment. Okay, every month, so it's a monthly thing for 2.5 years. 2.5 years every month. That's a total of 30 months. So there's our value of N is 30. Calculate the future value of the funds, provided they can earn 8% compounded monthly. So let's figure out what 8% is monthly. That's 8% divided by 12, and that will give you 0.67 or 0.66% per month, which turns into a decimal of 0.0067. Okay? So here's our basic formula. FV equals PMT 1 plus I to the N minus 1 over I. And we're going to take a look at it here. So here's the basic formula. And So here's what it will look like when you plug the numbers in. Future value is $75, which is the payment. 1 plus 0.0066 or 0.067. That's the value of I to the power of n, and there's 30 periods, 2.5 years at monthly, minus 1 over 0.0066. When you plug that through your calculator, what you'll end up with is 75 times 33.05, which comes to a future value of $2,479.20. In other words, after 2.5 years of a stream of payment of $75, considering 8% compounded monthly, this much money will be accumulated. Number 8. We'll take a look at number 8. So number 8 says EGLA plans to invest $175 every month. So the payment is $175. PMT equals $175. And every month by purchasing units of a diversified equity mutual fund. If the fund generates an overall rate of return of 6%, compounded monthly. Okay, so we got a payment monthly and a compound monthly. By definition, that's the simple. 6%, it will, what we're holdings be after 8 1/4. Now I got to be careful here because it is 1/4, 8 1/4 years. Okay, so you have to ask yourself a couple things here. We got to do some initial calculations. Seeing that 6% is compounded monthly, we got to take 6% and we got to divide it by 12, and that'll come out to 0.05 percent per month, which is 0.005. I think I'm right in saying that, 0.005. And 8 1/4 years, we have to ask, well, what is that in months? Because we're dealing with months here, right? Everything else is months. So 8 times 12 is 96. So that's 8 years is 96 months. And 1/4 of a year is 3 months. So I got 99 months. That's what I would tally up there. So in the case of number 8, if we plug the numbers into our formula, so here we go. The payment's 175. 1 plus the 0.005, that's 2 O's there, 2 zeros. 0.005 to the power of 99, which is the total number of months, which is the value of n, minus 1 over 0.005. And that comes to, if we do the mechanics on that, that comes to $22,346.66. If you look in the course, you will find that I have all of these worked out in video, these examples that I have here. So I've done 1, 5, 7, 9, and 13. So there it is right there. You can see the actual workouts. So if you want to see the mechanics of how it's done, I have it gone through in great detail right there. Any questions?